Hello and welcome to lecture 29 of Math 2R03. In today's lecture, we're going to be looking at section 6b on orthonormal bases. And in particular, we're going to be looking at the Gram-Schmidt process. So you may remember that from your first linear algebra course where we saw the Gram-Schmidt process. What we're going to be doing today, and kind of the unique thing is, not only are we proving Gram-Schmidt for the case that you did, but we're actually going to be doing it for any product space. So the Gram-Schmidt process is something that holds much more generally. So in this first part, I'm going to just kind of be setting up the notation and the definitions that we need, and then we'll talk about the Gram-Schmidt and its proof in the later part of today's lecture. So I'll make myself disappear again, and let's start kind of by introducing some of our terminology. And some of it may seem familiar from Math 1B03. So we have a list of vectors, and we're going to call them orthonormal if they have the property that any two distinct vectors are orthogonal, so they have the orthogonal property, but they also have the condition that their norm is 1. So when you're thinking of an example of an orthonormal basis, the standard example that you should think of is the standard basis in Fn. So the standard basis, not basis in Fn is orthonormal. So as we're doing today's lecture, if you're trying to think of something that's orthonormal, just think of the standard basis. That's your standard example of that. So what are some of the properties of orthonormals or an orthonormal set? Well, we have the following two properties, which are quite handy. The first is if you have a vector that's written as a linear combination of those orthonormal vectors and you want to find the norm of that, the norm is simply the length of a1 squared plus the absolute, sorry, I should be saying the absolute value of a1 squared plus the absolute value of a2 squared, all the way up to the absolute value of am squared. And the other property we have is that orthonormal sets of vectors are linearly independent. So let me give you a proof of these facts. Now for one, I'm just going to prove the case m equals 2. You can extend the proof that I give here more generally, but I'll just do the case m equals 2. So here we're looking at the norm of this vector squared, and look at we're doing a sum of two vectors, and by definition, right, e1 and e2 are orthogonal to each other. So we can apply the Pythagorean theorem. So this is equal to the norm of a1 times e1 squared plus the norm of a2 e2 squared, and this is called the Pythagorean theorem, or this follows from the Pythagorean theorem. Then the AIs are coefficients, so you can pull them out. So this is the norm of a1 squared times the absolute value of a1 squared times the norm of e1, and then the absolute value of a2 squared times the norm of e2, and these guys are squared. But remember, e1 and e2 come from an orthonormal set, so their length is 1. So this guy and this guy are both 1. So we're left over with the absolute value of a1 squared plus the absolute value of a2 squared. Okay. Now, as I said, I only did the case m equals 2, but to generalize it, it's not that much harder. Okay. What about the second property? Right. Well, let's say that there was a linear combination of the vectors that gave me 0, and my goal is to now show that each of these coefficients are 0. But if you look at, because this is equal to the 0 vector, we know that 0, which is equal to the norm of 0, which would be equal to the norm of this guy right here, the norm of the vector. And in fact, we can actually put squares here, right? It doesn't actually change any of the values. And then by part 1, this is equal to the absolute value of a1 squared all the way up to the absolute value of am squared. So these are numbers, right? These are actually real numbers, and they're all positive or zero, and they equal to zero. So this forces that the absolute value of each of these numbers is equal to zero, but that implies that each AI is equal to zero. So our linear combination can only happen if all the coefficients are zero. Okay, so now that we know what an orthonormal set is and two of its properties, I just want to define what an orthonormal basis is. So a basis of V is an orthonormal basis if the basis is also an orthonormal set. Okay, and so the standard basis is an example of an orthonormal basis, but just so that you have another example, if you can take 1 over root 2, 1 over root 2 as your first vector, and you take 1 over root 2, negative 1 over root 2, this is an orthonormal basis in R2 with the standard inner product, okay, the standard Euclidean inner product. Okay, it's a basis for R2, they're linearly independent, their norm is both 1, and they're orthogonal vectors. Okay, so we'll pause here and we'll set up some more properties of orthonormal bases, and we'll set up the Gram-Schmidt theorem.